Okay, so just problems today. Just to remind ourselves of what we're doing. We talked about angular momentum. What was the angular momentum density? It was G. It was epsilon naught E cross B. Okay. If you integrate this over the volume, it'll give you the total. Sorry, did I say angular momentum? Momentum. We will have angular momentum today. Well, that's easy. It's R cross P. Okay, so the example, we've done similar problems, but I just want to do a few more problems. So this is problem, I think, 8.6 in Griffiths. And you have X, sorry, this is Y, Z, and X, and you have a parallel plate capacitor. You know, we have so gotten used to taking finite parallel plate capacitors and whatnot. It doesn't even bother us anymore. We use those exact formulas. So this, as usual, there's A, which is the area of the plate, and I think D, this plate separation. Maybe I should do it here. Oh, plate separation D, and area A, and there's plus sigma minus sigma, so there's an electric field E. Now if we've done this sort of a problem. Sigma, of course, is a charge density, but it's important. Let me also write it as this way. It's the charge Q on a plate, on the positive plate. If it's a negative charge, I explicitly denote it as minus sigma. But you can do anything with this problem. For it to have momentum, I need a magnetic field. So you throw in an artificial magnetic field coming out of the board. It's inside here. So B. So obviously there's E and B, so there's E cross B, because they're not parallel to each other. So what is the momentum density? Density is epsilon naught. Sigma over epsilon naught, that's the electric field, right? And it is in the z hat direction cross B in the x hat direction. Oh, this is tricky. Cross and x hat. So let me bring out the sigma B. Z cross x hat is y hat. So then the momentum is the volume, but gosh, I take the density and integrate it, but there's no integration here, right? So it is sigma B area times length in the y direction. I took the momentum density and multiplied it by the volume. The direction remains the same.
Isn't that how we're going to use B?
Oh, yeah, thank you. Again, the usual story, this is static. Where is the momentum, right? It's stored in the field. There's something about the field that can hold momentum with static fields. So how do you fix this problem? So Griffiths does what he always does. He throws in a current, a loop, a conducting wire from here to here. Maybe there's a little bit of resistor. What's going to happen? Current is going to flow from here to here. and the plates will be neutralized. As a result, there might be a force on the wire. So this is a wire that is designed to discharge. Okay? So the force on the wire is going to be I dl cross B integration. Again, there's no integral to be done. All we have to do is find the direction. dl well, like I said, I L cross B. Nothing depends on position here. Let me do L first. L is D times Z hat. I is the rate of change of charge on this plate. Well, notice I'm going to put a little space here. Let me fill this out. Space D. I don't need to put anything more. I don't think. Why did I put a space? I'm going to do this. I'll tell you why. Here, Q is the total charge on the positive plate. So let me tell you why I put the negative sign. It's the U. Again, when we do capacitors, we do the same thing. If you recall, there's a current going this way. It's being discharged. What is happening as the plates are being discharged? What's happening to Q? Is it increasing or decreasing? On the plate. Decreasing. So it's a decreasing function. So what is dq dt? Plus or minus? Decreasing function. If you take the derivative of a decreasing function, it is going to be a negative number. The slope is downward. Yeah? The current is a positive number. It's the magnitude of that, right? So you stick this in. Yeah. So F is equal to minus dq dt times d times b z cross x, again, that is y hat. That's a force on the wire. Now, as the plate discharges, what is the total impulse transferred onto the wire? Well, as the plate discharges, impulse, what is impulse? Change in momentum. I have minus dB this is y hat dq dt, and it's going from plus q to 0. So that is minus b, minus db, minus db y hat 0 0 minus Q, that is Q dB y hat, and Q is sigma A. And then you realize that the two quantities, the impulse delivered onto the wire matches exactly with the momentum that was stored. So whatever momentum that the field had can be transferred onto the wire. Okay. That was one example. And then let's talk about angular momentum. Angular momentum is R cross P, right? So in here we'll define angular momentum. Exactly that way. You have to pick an origin, and R is computed about that origin cross G d tau. Yeah? So it is, so we need momentum for angular momentum. We need the ability for things to be able to rotate. Something circular. Our parallel plate capacitor won't quite do. It's not an easy thing to calculate. So here too, these are just great problems, fun problems, and how numbers just match up. I think it's example 8.4. So you have a solenoid. To show that it's a solenoid, what I'll do is I'll show the windings, not all of them. Yeah? So this is a solenoid. This has a radius of R. All of these things are very long, huh? Although I'm not going to draw it that way. Inside the solenoid is a small conducting cylinder. This too is long, okay? Don't mistake the small size for small. Otherwise, I'll be out of my artistic dimension. So this has a radius, A, and he puts a charge, let me make sure. Yeah, he puts a charge plus Q on this entire cylinder, plus Q. The whole thing is, of course, length L. But length L is, of course, large enough for our usual expressions. No fringe effect, nothing. The magnetic field inside a solenoid, we're just going to use mu0 Ni and things like that. And well, there is also an outer cylinder because he doesn't want to put electric field just everywhere in the universe. has radius d and a charge of minus q. Both the yellow cylinder and the green cylinder, the small cylinder and the big cylinder, they are free to rotate about the z-axis.
So are dotted cylinders, those don't rotate?
Yeah. The other one is actually solenoid.
Yeah.
So what are the fields so that we know mu 0, B is mu 0 n I in the z hat direction for values of z 0 less than or equal to s, less than or I suppose r. Correct? That's the solenoid. What about the electric field? Electric field, again, it's Gauss's law, lambda over 2 pi epsilon naught 1 over s in the s hat. It's the same electric field as that of a wire. But for what values? Nope. I don't particularly care about, I don't know about the technicalities at the moment, nor do I want to worry about that because I'm integrating over the volume. So in the intersection of these two regions, there is momentum. So let's do G epsilon naught. So G will have to be in the intersection, right? So I'll also make that clear. E 2 pi epsilon naught 1 over S times B mu 0 n I, and then the cross product S hat cross Z. And this exists for, is that true? Because B doesn't exist out here. I'm almost forgetting what I'm calculating. And so I'm going to calculate the angular momentum. Fine. So let's do this. Lambda. Everyone okay? So I just put the vectors outside. So I have 2 pi epsilon naught, but there's a mu 0 n I, and it's just 1 over S. What is S hat cross Z? Almost. So now let's compute the angular momentum. So I'll make this clear. The angular momentum, L, there might be, so this is 1 over S, so there might be an integral there. But let's see, let's do R cross G. R cross G is equal to S hat plus Z hat cross minus lambda over 2 pi. Oh, see, the epsilon naughts would cancel. Lambda minus lambda over 2 pi mu 0 n I over S phi hat. So first of all, I get these two, and I would get lambda over 2 pi mu 0 ni s hat cross phi hat minus z lambda mu 0 ni over 2 pi s z hat cross phi hat. What is s hat cross phi hat? Z hat, good. S hat cross phi hat, yeah, minus that. What is z hat cross phi hat? Negative s hat. So, I'm just going to say stuff I don't care about. Why is that? No, I don't care if there's an angular momentum in the s hat direction. It's not going to turn around. It's only free to move in the z hat direction. Correct? Even better, there's no position dependence here, so I don't have to integrate. Yeah? So let me write LZ as opposed to just L, because I'm only worried about the LZ direction. I have minus lambda over 2 pi, and at some point I need to check if I'm doing this correctly. The area, you guys tell me the area, and let me check, because I want you to think. Sorry, you guys think about the volume. What is the volume that I want? Inside of R. No need for it to move. These are, it's one area of one cylinder minus the area of the other cylinder. So it's going to be what? Pi r squared minus a squared times L. Yeah? Okay. So I have LZ is equal to lambda times L is the total charge Q minus Q mu 0 ni over 2 r squared minus a squared. Make sure I haven't dropped any terms. Minus Q mu 0 ni over 2 r squared minus a squared. Yeah. So now, a field has this much angular momentum. I want to show the same game that if I can discharge somehow, I want the angular momentum transferred by the discharge onto the rotating cylinders to be the same as that. That is my goal. Okay? So what we're going to do at this point, fine, leave it there. Now you let the current go to 0. what happens? There's an electric field that is induced. Electric field will be induced both inside and outside. So let me do this. When S less than R. Yeah? In B is in the vertical direction, so usual Faraday's law, E is going to be circumferential, so E phi times 2 pi S, this is the integral of E dot dl, correct, is equal to minus dB dt times the area. dB dt is easy enough, mu 0 n I dot times pi s squared. Because you're inside here, so it is whatever magnetic flux inside this small area. So then I can write it like so. This is, of course, induced. What can I do? I can cancel this, cancel that. I get minus mu 0 n I dot over S phi hat. Make sure that is true. Minus, oh, there's a 2. Oh, and the S is upstairs. 2 comes below, S is upstairs, so that's very important. Minus 1/2 mu 0 and I dot, it's a faint dot, S phi hat. Okay? Well, good. I'll just write this as E for not for induce, but rather inside where it affects this region. Yeah? What about E outside? The magnetic flux is a constant. So I think, and that's the difference. E phi 2 pi s minus mu 0 n I dot times pi r squared. Beyond that, there's no magnetic field. So then E out is minus mu 0 n I dot r squared over 2s times what? Again, check. Phi dot. Perfect. So, there is E in this region, En, and then there's E in this region. There's electric field and charges. What is the electric field going to do on the charge? Force. And force could even create a torque. So let's compute torque. So I will do torque on the outer shell. N is equal to R. S, ooh, I can do better. Where's the one? B. S hat. Do you realize the torque is only going to come with this torque, or do I need to write the other torque? The effective torque. Well, if you, this is the other term, right? And what is the see, the electric field is in the phi hat direction. What is Z cross phi hat? Z cross phi hat is S. It's not going to turn. I don't want to do this because this term will have an integral and I don't want to integrate. So cross F. F is Q times E. It is minus Q times E out, well, sorry, plus mu 0 n I dot R squared over 2, what's this? 2B. Then I have to do, yeah, I didn't do lambda times integral over dz because it's all constant. It's going to be q. And S hat cross phi hat is what? Z hat.
We lost our charge because it made it negative Q1, right?
Correct.
Just keep out there as negative Q1.
Yeah. Yeah, correct. So I just want to make sure I get this right. There's a b here, nicely cancels. Mu 0 n I dot R squared Q over 2 Z hat. And so let's look at the angular momentum imparted on this disk. Well, it's NDT. This is over a certain amount of time. So what do? It is NDT. This is perfect. I have dq dt. And so, sorry, di dt. So it is mu 0 n R squared Q over 2 Z hat di dt dt. It is going from I to 0. Yeah, we're discharging the current. And so I just get minus mu 0 n R squared Q over 2 I Z hat. Let me check that as well. Mu 0 n R squared Q I over 2 Z hat. So just like the outer cylinder, the inner cylinder will also feel a torque and an angular momentum imparted. I'm not going to repeat the calculation, but the angular momentum imparted on the inner cylinder is given by ½ mu 0 n I Q A squared Z hat. And this is, you verify this. Yeah? Therefore, total momentum it? Well, it's the sum total of this. You know what I'm going to do? I'm going to cheat. And I'm just going to look over here. But we know how to add. Oh, it's LZ, so I don't need to put Z hat. The same thing, nice balance of things. So you have to find, to understand these things, you should get realistic problems. And for realistic problems, we need exact expressions for electric field and magnetic field. So we're restricted to these infinite wires, cylinders, parallel plates, solenoid. I bet you that a clever problem could also be done with a toroidal magnetic field. But generally, and the whole point is to show that indeed there's a balance between energy gain here, energy lost there. Momentum gain here, momentum lost there. And the curiosity of how a static field can hold momentum and angular momentum. Yeah, that is something that up until a couple of days ago would not have entered our discussion. Okay. Oh, I'm uncharacteristically early today. We have 8 minutes left. Happy Friday.